Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 15, Python module written in Rust, coming from the previous episode where we spoke about context managers. So basically what we'll be doing now is a proof of concept implementation of how to get hopefully faster implementation of code in Rust to be running in your Python code. So first we'll compare the speed of the algorithm in the two languages. Then we'll compile it into a Python module, but using the language Rust. And at the very end, I will give you a glimpse on how to use your now newly compiled Python module in Python. The useful crates for this endeavor are Rust CPython, the Py03 or PyOxidize, and the setup tools in Rust. And the last one will help you to package this up nicely for your end users. So if you are writing a high performance library or anything that you've already written in Rust, but you want to make it accessible to Python users, this will help you greatly. Let's look at the code and the algorithm to do the speed comparison. The algorithm is a silly method to compute the number pi. What it does is it generates random points and tries to figure out if those points are in the unit circle. If they are, then it gets added as a point was found. And at the end, we just compute the ratio of how many points were found in a unit circle and how many were not. Then we multiply this by 4 to come up with the whole circle to get an approximation of pi. This is not efficient, of course, not a precise way to compute the number pi, but it is a good way of showing how you can speed up an embarrassingly parallel problem using multiple computing cores, multiple threads. And of course, it's a good way to quickly show the difference between a scripted language and a natively compiled language. Now, in order to pull this off in Python, we will need our math module, the random module, to get the random numbers. Time we use to count the time this algorithm is running, because you want to compare the speed, right? Then we have two options. I use concurrent futures and multiprocessing to have two ways of running this with multiple threads or with multiple processes. And I use the psutil external module to figure out how many CPUs the machine has, because this way you can use the full potential of the computer by using all available cores or even virtual cores. Let's look at the wrapper function. So the first thing that we have is this Monte Carlo Pi that gets the number of iterations. So how many points we want to throw into the air to figure out if they are within the unit circle. Now, the number of CPUs, I include the ones that come with the hyperthreading one, because that's also what the Rust side of code will do. Then we start the timer for our computation. And the first thing we start would be the threaded one. Then here I have as an alternative the multiprocessing one. Then we stop the time. We get the total number of iterations. We get the computation of pi. And at the end, we compute a string that is a nicely formatted way of the big number that will show us the number of computations per second. This is just a wrapper function that will be called by something that writes this for us to standard out. So we return a tuple that holds a pi that we computed and the formatted string with our computations per second. Now, below that, we have the actual computation that we can then call either in the threads or in multiprocessing. Let's jump down a bit to see that code in action. Here we have the range. We get our random point. We check if it is inside the circle. If it is, we increase the number. And in the end, we return the number of the ones that we found to be within the unit circle. If we now go further down, here we have first the multiprocessing and after that the threading version. So we have the multiprocessing one creating a pool This then runs this Monte compute for the iterations. So here I create an array with the number of CPUs to then run in parallel this compute function. Then we get the total number inside, and this is then handled by the wrapper function that we saw before. The multi-threading one does a similar thing, but it uses a thread pool executor. We add a task, so we have the Monte compute task that gets the argument iterations handed over for the number of CPUs that we have. We build the sum of the results from our tasks, and we get the total number returned. So these two functions do the same thing. At the bottom in the main function, we actually time how long this whole thing takes to get an idea of how fast this Monte Carlo Pi works in overall. And we get our runtime of the function. We get pi printed out, so we see if the calculation makes sense. And then we get computed the computations or calculations per second doing our Monte compute thing. Let's run it. This will be running the Python version of this function. And you can see the total runtime is 3.36 seconds. And it computes something that is close to pi, 3.14, close enough, I guess. And we get about 2 million calculations per second. On the Rust side, we do the same, basically, but in a more compact fashion, because we get to use a closure to do it. So we use the num format to get a nice formatted string for a big number. We use the randomizer, threading, and to time the whole thing, we use the instant. So we do the same thing as on the left. Let's hop back over to the Python code to compare. So now this Monte Carlo Pi and the Monte compute is basically wrapped up in this big function here. We get the number of CPUs, we start the timer, then we initialize a vector that holds all the handles of all the threads that we spawn. So for every CPU found, we spawn a thread that creates his own random number generator. And then within the iterations, we create a point. We check if it is in the circle. If it is, we return the points we found to be inside the circle. And then further down, we have the same algorithm going as on the left. So we have the computation of the total points found, and this matches these computations. And you can see that this is just a library. I do not have a main function here. This will be useful further down the line. In order to run this code, I have created an example. What we do here is we import our crate and the function that we've created to compute the Monte Carlo Pi. And we also use the timing to get to the same as we have in the main function of the Python one. So we start the counter, we start the timer, we run Monte Carlo Pi with 1 million iterations, we get a tuple back, so pi and our calculation strings, and here we have the output. If we run this, we can quickly do that by using cargo run example pi, and it will compile, run the example, and we get an output. If we now compare the two, we can hop over and quickly check the output again that we have for our multi-threading version in Python. So Python is quite a bit slower, but we haven't used the full potential of Python yet. Let's switch over to our multiprocessing version. So if we go to line 17, and now we are going to use the multiprocessing version. This will now actually use all of the cores because of the global interpreter lock. Python is actually restricted to one core only if you use multiple threads. Now using multiple cores, using the processing will be much faster. And especially in this case, because this is an embarrassingly parallel problem, we do not communicate between the processes or threads. This should be scaling fairly nicely. Let's run this. And we can see this is now actually faster than Rust. We don't need to compile the module, and therefore we can stop this episode. But that's not true. I forgot to do a very important thing. So this is by default the unoptimized debug version. We will now run this in the optimized version. So we add release to our cargo run arguments, and this will be rebuilt. And now you can see that there is a significant improvement in speed versus Python. So this is the fastest that Python can give us, 1.11 seconds and about 7 million computations per second. This is the Rust version, so we are done in a fraction of a second, and we get 460 million calculations per second out of this. And in both cases, we get 3.14, something that resembles Pi a little bit at least. So it is worth it to make this a Python module that is compiled in Rust, because this will significantly speed up our computation. Let's do that then. So we can exit. On the right, I will switch over to the first way of how you can pull this off. So we go to Pi, Monte Carlo Pi, and we open the cargo toml file. The most important thing that you have to do if you want to write a library is, besides using cargo new --lib, is to add this lib section. Give your library a name. So I chose Monte Carlo Pi in one go, no underscores. And you have to change the crate type to be a dynamic library. Then, since we want to use our native code in Rust that we've already written, I'm using my crate from this location. So just the parent directory and then into my crate that I've shown before. And we have the CPython dependency. So in this case, I'm using the CPython crate to create an extension module. You get to use the version of your preference, and you have to add the feature extension module. Once you've done that, you can hop into your library code. Let's do that. So source librs. Fairly compact affair. We have the CPython crate and all the needed macros and result types. And then we have our own function that we want to use. Here you have to use the same name that you've used in your cargo toml. Otherwise, the library will not work in Python at the very end. It will compile fine, but you will not be able to import it. Here they add a docstring. So this is the first m.add that happens. Then you will add a function that will be called sum as string. This macro will then reference to this sum as string underscore pi that will have the correct types that Python needs. So how does this work? Here you can see the native Rust Python function. So this will take two numbers and return a string, fairly simple. This you could use in your Rust code normally, but here we have the same thing written in a way that Python will like. So you hand it this Python instance. You get to use your two arguments that you have here too. You use the Python result type, and then you can call the native function and return a result OK. And this is how this works in principle. You can use your native code that you've written somewhere. So in our case, this will be our Monte Carlo Pi function actually. Wrap it in a function that Python will like from the input and output types, and then you add it in your Python module initializer macros madd list. And this is exactly what I'm doing here. So I madd as well a function that I will call only mcpi, so I don't have to type so much. So mc for Monte Carlo and pi for the number pi. And I've written my wrapper down here. Also takes this Python thing, our iterations, it returns a Python result, which will be a tuple. So here we have our pi computed, and this will be the string of calculations per second. As you can see, this looks very similar. It does this for us. Now, if we want to run this, what we have to do is, of course, build this with the release mode because we want to have the high performance. And this we can easily do by using cargo build release. This will now compile the module for us, but this does not mean you can use it straight away in Python. In order to do this, I will hop into the shell. In the shell, you can see from my previous tests, I have this Monte Carlo Pi.so file, but this is not generated by cargo's output. What you will end up with is a file called target release. In the case of macOS, lib Monte Carlo Pi dynamic library, you will be able to see that in Linux called .so. And if you want to use that, you will have to copy it from there because you cannot use this lib prefix actually. Now let's do that. So we will copy target release lib Monte Carlo Pi lib to the Monte Carlo SO. And once we have that, we can actually use Python, and we can use import Monte Carlo Pi, and we can run our mcpi function, and we get an immediate return because the Rust code is returning in fractions of a second. And we can run this multiple times even. Right. Now, there's another way to do this using the Pi03 crate. That makes it a bit less syntax sugary because here you have this Pi module initializer. You have to write things kind of double, and you have to remember that you have to use the same name. Let's switch over to this code. This means we go to Pi03, Monte Carlo Pi. Here we have the same thing happening. You have to add the lib section, do the dynamic library, give the name. Then in this case, we use Pi03 as a dependency. Again, our own Monte Carlo as well. And we have to use the extension module feature. Then we can just look at the code, which will be much shorter and cleaner. We get the prelude, we get the wrap pi function attribute that will then be a proc macro that does the stuff for us. Now, we use also our function from our Monte Carlo lib. Here we have the attribute that uses a proc macro that makes this a Python function for us. So this will for us add this extra Python argument that we need. And this returns a Python result with our tuple. So here we have our pi and the string. All we have to do is now make this a result, calling our function and the iterations that were passed in. And here we have then the Pi module definition. This is basically using the Rust syntax that exists already. So you define a function that has the name of your module, so Monte Carlo Pi. You use the attribute proc macro Pi module to make this a module, and then you can use the madd function to use the wrap pi function macro to use mcpi, so our wrapper. And then this will create a Python module with the name Monte Carlo Pi that holds a function called mcpi. So we have the same result as we had before. We can hop over to the shell, to the Pi03 version, and we can run the same thing. So we run the cargo build release. And once this is done, we also have the target release with this dynamic library name. So we have to copy, which we already did. So let's repeat the process. We can start the Python shell again. We can import the library and run our amazing fast implementation of this algorithm. I hope this quick introduction in how to speed up your Python code with optimized compiled libraries in Rust was helpful. As you can see, this is fairly easy to do, especially with the PyOxidize crate. You might prefer to use this one. There are many solutions out there that will help you. Thanks for watching. Coming up next at the From Python to Rust series will be the other way around. We will be using Python within Rust.